Okay, before we get started, because I've got everything set up, I'm just waiting on the computer, the projector to light up. Does anybody want a student planner? I've got a whole stack of them for this year. Use it to keep up with the due dates. Who else? Anybody else want one? I got a couple more if you come by my office. And hopefully that's enough. Everybody can see that pretty well. Excuse me. So in section 11.3, we talked about rates of change. And just to go back for just a little bit of review, this is the last problem that we worked on. It was an applications problem. And the basic conclusion that we had was that the way that you find the instantaneous rate of change, and this is going to be where we're going to pick up in 11.4, we're talking about the definition of the derivative. The instantaneous rate of change is the limit, as h approaches 0, of the function of a plus h minus the original function f of a divided by h, where h is just a number that's really close to 0, but can't be 0, because if it is 0, then we're going to divide by 0, and that causes us to have an undefined situation. So we are ready now to talk about the definition of the derivative. And all we will do in chapter 12 will be applications and learning how to take derivatives of functions. But this is the definition of derivative. Okay? This is what does a derivative mean.
Can we get this, is this PowerPoint available to us?
It should be in 11.4, Shelby. Let's check. Should be.
I couldn't find 11, I just probably don't know where to look. I couldn't find 11 point, like any of the lectures. 11.2, I don't know if that would ever got.
11.2 is not there. I've got to completely redo 11.2. The only thing you have is what we did in class. But 11.2, you really don't need necessarily the whole PowerPoint, because the core idea of 11.2 is that you're trying to determine 11.2, is a function continuous or not? And a function, without even talking about calculus, without considering calculus at all, a function is not continuous anywhere you have to pick up your pencil to move over somewhere it's undefined. So a function is not going to be continuous when it approaches positive infinity from one side and negative infinity from the other. And it can be vice versa. It can approach positive infinity from this side and then from this side negative from this side and positive from this side. Or it can simply be where there's a hole in the function, where the function is not defined at one single number. But the test for continuity is simply, first of all, if you're trying to test for continuity at some value of x, like maybe it's 2, then is f of 2 defined? And that's a yes or no, it is or it isn't. Either you're going to have to divide by 0 with it, or you're trying to take a square root of a negative number with it, and that makes it undefined. So is it defined? Does it have a value at x equals 2? If the answer is yes, then you continue on to the next step. If the answer is no, then you say no, the function is not continuous at x equals 2 because f of 2 is undefined. But if you said yes, then you move to the next step. And the next step says, does the limit from the left of 2 equal the limit from the right of 2? And you can determine that looking at the graph. Basically, the bottom line on it is when you take the two limits, do they come together? If they come together, then they are equal. And the answer to question 2 is yes. And if the answer to question 2 is yes, then you move to question 3. If the answer to question 2 is no, which means it did this, and they miss each other, or it did this, they definitely missed each other, then the answer is no, and you say no, the function is not continuous because the right hand does not equal the left hand limit.
I get all that, there's just some homework questions that we never talked about, like just some different finding.
Okay, on the ones that you're stuck on, and this is for everybody, not just you. On homework questions in any of the sections, there should be the option over there for you to click in My Math Lab, Ask My Instructor. And if you'll click that button, I get an email, and the first thing I do after I get home in the evening, after I've, kind of taken care of chores, is I check my email, and if there's a question from a student there, I go ahead and look at that question, and most of the time if it's something that I can just say a few words about, then I'll just reply to the email. But if it's not, then I'll actually go to the question and I'll turn on my recorder and I will record the answer to that question, and then I'll tell you, go look in Show Me on whatever folder, because I posted it for everybody to see. That way, if everybody asks for problem 13, I don't need to do problem 13 20 times, I need to do it once and then show everybody how to do it. Does that make sense? Okay. But use that Ask My Instructor button, because that's what it's for. And if you really are in a hurry to find out, you can't wait until in the morning maybe, you really need to know tonight, click Ask My Instructor and then follow it up with Remind. And then I'll go check my email and find your problem. So let's see, in now your stuff that's already due is all about the bottom in Show Me. So at 11.2, the only thing you've got is the PowerPoint and the homework, because I never could get anything to go up there. And 11.3, you've got the lecture instead of the PowerPoint. Now, if you want the PowerPoint, I can put it up there.
Yeah.
Okay, let me do it right now.
So the lecture for 11.2 hasn't been uploaded yet?
No, it hasn't. The only thing I've got is what we did in class. I think I do have that, and I can load it up there.
Yeah,
But it's not the whole chapter. It's not every single problem. Okay, so there's your PowerPoint from last time. Okay? Let me see if I can find the little short thing for 11.2. Okay, so here's the video for 11.2.
So now, and just to recap, so it'll be in the recording, our tests for continuity are, is f of c defined? And in this case, c was -3. And is f of -3 defined? Yes, f of -3 is 4. So yes, that step checked out. And then our second step was, does the limit as x approaches -3 exist? And we have to break that down to the question, well, does the limit as x approaches 3 from the negative side equal to the limit as x approaches -3 from the positive side? And we saw, looking at the graph without having to do any math, that if I approach from the negative, I approach 4. And if I approach from the positive, I approach 4. So that tells me that the limit as x approaches -3 from the negative side is 4, and the limit as x approaches -3 from the positive side is 4. Therefore, that limit as x approaches -3 is 4, because these two match. So then the last step is to compare your answers to 1 and 2 and say, do those two answers match? Is the limit as x approaches -3 equal to f of -3? And the answer is yes. Both of those were 4. So therefore, that function was continuous at x equals -3. Now you can prove it's continuous at any other point as well, but I chose particularly to look at this point because that's the one point where it did something weird. Okay? Something that was kind of unexpected. So let's work through the second example and apply the rules.
Okay, and hopefully you remember this from class now.
This is, I
So in the
understand
second
all this stuff,
example,
I
we
just-
have
there's
this
stuff that we
function.
never talked about that I didn't, like,
Okay. This is the part that you probably need to watch then.
And
And I'm
our
supposed to
first
show you.
question-
Maybe you were not here the day we did it in class.
I haven't missed a day. I don't have, yeah.
Is
Okay.
f of, and the point we're interested in here, obviously, I would hope, is -1. So is
So
f
that's actually
-1.
from YouTube. And the link to it is right there. Okay, so we are going to talk today about the 3 major concepts in today's lesson. Number 1, what's a tangent line? And how can you find its slope? Number 2, what's a secant line? And how do you find its slope? And then number 3, what do limits have to do with finding the slope of a tangent line? Because the slope of the tangent line, by definition, is a derivative. And that's a brand new calculus concept for all of you. So let's talk first about the tangent line. Make sure we've got all of our ducks in a row as to what a tangent line is. And in geometry, a tangent line to a circle, and we're using a circle because it's a curve. It's a curve everybody's familiar with. A circle, tangent line to a circle is defined as the line that touches that circle in only one point. Now that point can be anywhere on the circle, but it only touches the circle in one point. And if it only touches it at one point and not any nearby adjacent points, then what we say that it does is that it indicates the direction that whatever the circle's equation is, the direction that equation is moving. Is it moving positively? Is it moving negatively? In other words, we're talking about the slope at a given point. Okay? So what we're going to do is we're going to look at some tangent lines. Now, some of these lines are tangent lines and some are not. So we need to figure out which ones are tangent lines and which ones are not. So remember, the definition is that it touches in exactly one point. But, this is an important but. It touches in exactly one point, but it does not intersect or cut through. What you think of as intersection, yes, it touches in one point, but it actually crosses over. Okay, it doesn't touch and go on. It actually fully crosses over. So in this case, the line P1 only touches that curve in that one single point. So P1 then is a tangent. Okay? And by the restriction that we have here, P2 cuts through. It actually intersects at P2. So since it cuts through, P2 is not a tangent line. In fact, in geometry, P2 would be called a bisector. It cuts it into two pieces. Bi means two and sector means pieces. And for the same reason then, P5 here is not a tangent line. So is P3? Yes. P3 is a tangent line because it touches it in one point. And the key idea here is that it kind of gives you an indication of what direction the curve is turning at that point. Because if you look at P3, it has gone from being negative, very, very negative, because its slope is negative, it's coming down pretty rapidly, to continuing to be negative for an instant, but then at some point past P2, it's actually going to go back to being positive. And with P1, the curve is basically going uphill, 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 uphill. So that's a positive slope. Uphill's positive slope, downhill's negative slope. P2 here, this line does not indicate what the curve is doing at that point. It only shows you what that piece of a line is doing. It doesn't match what the curve seems to be doing. Because what the curve's doing as you get close to P2 is it's going downhill, 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 but P2 is going uphill. So it has a positive slope. So that's why it's not a tangent line. And the same thing here with P5. The curve is actually going downhill, but P5 is a vertical line, which indicates it would have undefined slope. Now the real question comes up, and we're not thinking in math terms here. We're thinking in visual terms, because most people are better at the visual terms. The real question comes up with what's going on at P4. So we're gonna go for the two questions. Does P4 touch in exactly 1 point? Well, actually, it only shows you the one, so we're gonna say, yeah, it touches it in 1 point. Now here's the problem. Even though it only touches it at 1 point, does it cut through the curve?
Yes.
Yes. It does cut through. It starts out on this side and comes out on the other side of the curve. It actually cuts through. So P4 is not a tangent line or at least it doesn't appear to be. That means when we have points like P4 and we're talking about slopes of tangent lines, we're going to have to be careful. Because remember, I said the idea of a tangent line was it tells you what the curve is doing around that point. And in this case, in P1, the curve is doing the same thing that P1 is. It has a similar slope. And at P3, the curve is doing kind of what the slope of P3 is doing. It's basically decreasing or having a negative slope. And the truth of the matter is, what's this curve doing as you approach P4? Is it increasing or decreasing? It's increasing, so it has a positive slope. Does P4 have a positive slope? Does that line segment have a positive slope? Yeah. So this is kind of ambiguous. So this seems like a good way to eliminate them until you talk about points like P4. So we're going to have to come into a more detailed, rigorous definition than what we have. So this is a good starting point, but calculus lets us refine that starting point, and it will still agree that this and this are tangent lines. This and this are not tangent lines, but in fact, we're going to talk about whether or not maybe P4 really is a tangent line. Okay? So the next thing we're going to look at and this is just a point that I want to make with you. One of the reasons lines P2 and P5 are not tangent lines is because they didn't indicate the direction of the curve. Not just because they cut through, but they made no indication of what the curve's direction was at that point. Now for P4, like I said, we're going to have to define the idea of a tangent line a little more carefully. So before we try to define that, we're going to talk about a secant line. Okay? So the next thing we'll talk about is going to be a secant line. And how is that different from a tangent line? Okay, here's a secant line. And this secant line, notice the main difference in it and a tangent line is the secant line actually touches the curve in 2 points.
Where is the, I'm talking about the secant line notes.
Let me pull the notes up to see.
Oh, I actually.
Did you find it? Okay, so here we've got a secant line. And by definition, a secant line is this straight line here. That secant line cuts through that curve in 2 points. Now, I don't have the equation of that curve, okay? But I know that the idea of A and f of A is usually kind of ambiguous to people. You look at it and say, okay, what's A? You know, give me numbers. I like numbers, right? I like numbers too, I don't blame you. So let's say that A, instead of being A, let's say that A is 3. And then maybe this value here, although H is supposed to be a very little bit, let's say that this is 3.1. This is not to scale, that's 3.1. So in this case, let's say R of the point R is 3, comma, maybe that's 1. So f of A is 1. And then we're going to go to 3.1, so coordinates of S, because this is R, is 3.1. And when you plug into 3.1, instead of getting 1, maybe you get 2. Okay? Now, if you've got these 2 points, can you find the slope of that secant line? Assuming that we did actually have numbers there, what is the slope of that secant line? Well, it's the y values on top and the x values on the bottom. So 1 minus 2 is negative 1, and 3 minus negative 3 is negative 0.1. So the slope of that line, and again, this is not to scale, so don't try to make anything out of the scale. The slope of that line would be positive 1 over 1/10, and 1 over 1/10 is 10. So the slope of that secant line through these 2 points is 10.
So if I pick 2, let's say I pick 5 for A, would it come out the same way?
It would still be the same way, because this one will be 5, and this will be 5 plus a little bit, which we would usually start out at being 5.1. Okay? And then obviously, whatever this y value were to be, this one's going to be more than that.
So you could plug in any number for both of those and turn out the same.
Exactly. You can plug in any number of both of those, and it will come out the same, which leads to what I'm going to show you now. Regardless of what those numbers are, if you take R to be A, comma, and the function value for A, and if you take S to actually be A plus H, that H being just a little bit more, and then the function value of A plus H, then in order to find the slope of the line that contains R and S, then the slope of that secant line regardless of what these values actually are, using variables to represent them, the slope is going to be the ordered pair AF of A and A plus H and F of A plus H. Because that's the definition of slope, is that we subtract the y values and we subtract the x values. Okay, and is everybody with me so far? This is the change in the y values, regardless of what value we're actually starting at. This is the change in the y values, this is the change in the x values. Okay? So the slope of that secant line is actually f of the rightmost point, because it's a little more, minus the original function value, divided by, if you have A plus H minus A, what happens to A? Cancels out and they disappear. This is the slope of a secant line. That's just your standard slope formula with function notation for your 2 points.
Is that something we need to have memorized?
No. No, I want you to understand this. It's not a memorization thing. You need to understand that when I'm talking about the slope of a secant line, this is what it looks like, and that's because it follows the form that you've known forever, ever since you talked about slope of y minus y1 over x minus x1. That's what you've always been told that slope is, right? That's how you calculate slope. So all we're talking about here is the slope of a line that has 2 points in common with some curve. Now, to go further with that, I want you to look at something that's going to happen. This is an applet from Math Insight, because it'll give you an idea of what we're going to be doing here in a minute. This is exactly what we've just been looking at, right? We're starting out at the point x sub 0, which is x sub 0 is the beginning, and its partner y value, and we're going from there up to x sub 0 plus a little bit. Now basically what we have happening on this first one is that the change in x is listed as 1, and the change in y is 1.60, so 1.60 over 1 is 1.60, and that's the slope of that secant line. But what happens, and this function actually has a name, this is f of x equals x squared. What would happen if I were to move this point closer to the other point? Does that change the slope of the secant line? Yeah. What if I moved it closer still? Does that change the slope of the secant line? Okay, what if I could move that point close enough until actually that second point is right on top of there? What kind of a line do I have now? Because remember, this shows you secant lines. Can I have a secant line if R and S are on top of each other? No, that's a tangent line. And that's what this is saying. If you let, and I'm going to move this on up to trying to get to 1. Actually, I think I can type in 1. So here is the point 1, f of 1. And I've told it to increment, oh shoot. So are those 2 points close together? Because the first point is 1, 1, and the second point is actually 1.1 and 1.210. So are those 2 points closer together? than what the original points were. Yeah, there's only a little difference between them. They're really close together. Is it still a secant line? If I try to connect them, can I still make a secant line? Yes. But what happens if I try to put the point closer and closer and closer and closer? Is that when I get one point on top of the other, I can't have a secant line anymore. I would have to have a tangent line. Now, you can go back and play with this. That's why I actually gave you the link. Let's talk about why I want you to see that. To find the slope of a tangent line, I'm going to show you a picture of this in a minute to give you an idea of what we're doing. The book's definition says the slope of a tangent line is the limit. Notice this was the slope of the secant line right here. Agree? That was assuming we had two different points, A and A plus H. So this is the slope of the secant line. But what happens if we take the limit and let H get really, 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 really small, but not zero? Would we be closer to the slope of a tangent line if H was really, really tiny? Does that make sense? Because it means that your beginning X is getting really, 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 really close with the ending X. Now that's a math definition. Let's look at a picture. This line is a secant line. Agree? Is this line is that a secant line? Is it still a secant line? What's the actual difference between this line and this line? How do they differ? And what do they have in common? What do they both have in common? Their starting point. They both have in common the point R. What do they have that's not in common? Their slope is not the same. And is it, using these 2 points, tell me why it's not the same. Why are their slopes not the same? Well, because the second point is not the same for both of them. Their first point, this point, is the same. These 2 points don't match. Because as you go from having it through that point to having it through this point is closer to the beginning point than this point was. Does that make sense? The reason their tangents aren't the same, or I'm sorry, the reason their slopes isn't the same is because this point and this point are different points. The slopes are not the same because S1 is not as close to R as S2 is, because here's S1. And it's that far away. But if you move to S2 is closer to R. Okay? Basically, it's saying your secant line's shorter. And then again, what happens is that if you have the secant line here and its slope is M2, and I want to talk about this secant line, which is through the point S3, which is closer to R. S3 is closer. So they don't have the same slope either, do they? One more time. Here's S4. I'm going to draw the line through R and S4. Which is closer, S3 or S4? S4. Do you remember taking making a table where you're trying to approach, let's say this was 1, and you started out here at 1.1. So you first started at 1.1 and you found f of 1.1. And then you went and said, okay, what if it was 1.01? And f of 1.01. And then you went, well, this is f of 1.1. Okay, that's that very first point. So then you move closer to 1.01. And then you move closer by, what did you do to the next one? How did the next one look? Okay, 1.001. So we found a y value for 1.001. Well, then that point was 1.1. Now here's 1.001. And then your next step was to add another 0. And that gave you this point. Okay? And we said that you could move closer again and closer again. What were we doing when we did this? What was the purpose of making that table? What were we letting x approach? Like that, we're taking the limit as x approaches 1 from the right. Okay? As we take the limit as s approaches r from the right, what we're doing is we're using the slopes of the secant lines to come as close as we possibly can to what we want, which is the slope of the tangent line. The line that contains only r. Because the line that contains only r and has r in common with the curve, the tangent line's slope at one single point, xf of x, is the same as the slope of the curve. This is how you can find the rate of change at any point on the curve. Everything you came to before now, we talked about the slope of a line, because the slope of a line is constant. It never changes. But the slope of a curve changes every time you move forward or backwards on the curve. Here it's negative, 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 negative. Starting to be positive though. Now it's positive, 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 positive. So right about there, it changed directions. Okay? So the slope of a tangent line at some point is equal to the slope of the curve, and the way that we can find it is we take the limit as some other point gets closer and closer and closer to the point of tangency. So that's what this section is all about conceptually. That's the idea. Now the mechanics of it are not difficult. The algebra, okay, it stinks. I'm going to tell you that up front. The algebra part of this stinks. And it's the part that, as I've looked at your prerequisite skills quizzes, that's the part some of y'all are struggling with really badly. So now here's your chance to get that practice in that will straighten you out on that. So we're going to go through this conceptually, then we're going to practice the algebra a little bit. So what this one says, consider the graph of f of x where x squared plus 2 is f of x. Now this is a, what kind of equation? Quadratic. What do their graphs look like? Okay, arms up. A parabola, a curve. What does this tell you about that parabola? It's been shifted up on the y-axis by 2 units. That's the only thing. It looks just like every other f of x, or every other curve that's x squared, except it's 2 units higher than the one that's just x squared. That's all it is. We want to find the slope and the equation of the secant line, secant, cutting through 2 points, where x is -1 and x is equal to 2. So this is how you do that. First I need f of 1. I'm sorry, -1, f of -1. So that would be -1 squared plus 2. So f of -1 is 1 plus 2, which is 3. So that first point is going to be -1, 3.
Why is it -1?
Because that's just the point they told us to use as one of the points.
On our homework paper, it says +1.
Okay, we can fix that. I'll make it match. I didn't realize it said +1. So we'll just get rid of the negative sign, 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 get rid of the negative sign. And 1 squared plus 2 is still 3, right? That's one of the neat things about parabolas. The positives and the negatives are the same on both sides. Okay, now the other point is yours 2. Does yours say 2? Okay. So f of 2 is 2 squared plus 2. So f of 2 is 4 plus 2 is 6. So we have the point 2, 6. Okay? Now if I were to graph that function, I'm going to try to graph it here for you. I've got one, but I think it's got the -1 on it, so we're going to try to do it this way. If we were to graph that function, this is what it would look like. Now, because that's a parabola, and parabolas are only really, really, really curvy, kind of at the bottom of them, I want you to notice that as I'm drawing this secant line, I want you to notice how close to actually the curves behavior it is, even for a secant line. So there's my secant line. Let me extend it down a little bit more. So that red line is my secant line. And they want me to find the equation of that secant line. Now there's two ways to do this. Those of you that had me for 1630 know that I know how to do both, but I like one more than the other. You can use the point slope form. Which is okay. But ultimately, since if we're going to graph it, we really want y equals mx plus b. That's my favorite way to find it. So I'm going to take y equals mx plus b, and the first thing I need to know is m, using those 2 points. If I can find m, I'll fill in the slope. And m's not too hard to find. Because m is the difference in the x's on the bottom and the difference in the y's on the top. So this point, the x goes on the bottom would be 1, 3. And this one, the x that goes on the bottom, this one will be 2, 6. And the key is just remember that you got to keep those two together. So 3 minus 6 is negative 3. 1 minus 2 is negative 1. That means the slope of that line is 3. Are we in agreement? Don't trust my arithmetic. When you get points, if you catch me, I make a mistake. Is that the right slope? Okay, so we know in the equation of that secant line that the slope is 3. We have a choice for x and y. Which choice do you want? 1, 3 or 2, 6? You tell me. You want 1, 3? Okay, using the point 1, 3, x is 1, y is 3. And here's the only thing we don't know. What's the value of b? Can you find that? Three times 1 is 3. Subtract 3 from both sides. 0 equals b. So looking at y equals mx plus b, y equals 3x plus 0. And since we don't usually write down that 0, even though, if you notice down here, when I extended the line, that is the right y-intercept. There's the equation of the secant line. Okay? Now this was not calculus. This was not calculus. This was something that I just got finished giving a test to people in Math 1630 on. So this is back to something you learned in finite. That's why I told you, if you can't do those prerequisite skills, you can't do the calculus part. That's why you've got to pass those prerequisite skills.
Well, there's like 4 steps in the problem, really only one of those steps is calculus based.
Pretty much. Pretty much. In most of the problems, you're going to find that when we're actually getting into the calculus, the only step that's going to actually be calculus is going to be step 1. Everything after step 1 is algebra. So if you don't have your algebra background, it's going to come back and haunt you now. You'll have to get better at it again. So now we're gonna move to this idea. Consider the graph of f of x equals x squared plus 2. Same one we just looked at. I'm actually gonna sketch it back up here for you in a second. Just gonna kind of trace over it so we got it in front of us. And we're interested in the slope and equation of the tangent line this time at the point x equals, and we're going to stick with what we had a minute ago, we're going to stick with positive point. Okay? So at x equals 1, we have 1, 3. And it says, find the slope and the equation of the tangent line. Now remember, the only difference in the two is to find the slope of the tangent line. We use f of a plus h minus f of a over h and take the limit as h approaches 0. And in this case, a is equal to 1. Okay? So starting out, we're going to do f of 1 plus h minus f of 1 over h, and we're going to take the limit as h approaches 0 once we get finished. So the first part of it that we're going to need to do is we're going to have to do f of 1 plus h. And this is our function. So we're going to have to find this part. So what we're going to find, and we're going to kind of do this up here on the top for some scratch work, f of 1 plus h is equal to, what does the function say we do to 1 plus h? We square it. Plus 2. We add 2 to it. What is 1 plus h quantity squared? And no, it's not 1 squared plus h squared. And I warned you that last time. Twirl that out for me. What is it? Very good. Plus 2. Can we combine any terms? Which 2? We can combine 1 and 2, so that's equal to 2h plus h squared plus 3. Now we already know f of 1. F of 1 is equal to 3, right? Okay, what happens when you have plus 3 and minus 3? They cancel each other out. They're gone.
Hold on, where'd you get that 3 at? Is that from the previous part?
That's f of 1.
Okay, so when x is 1, where's?
Y is 3. Okay? So that 3 cancel that 3, and all that's left in the numerator now is 2h plus h squared over h. And at this step, what we desperately want, because we cannot let h be 0. What we desperately want is to get rid of that h so we don't have to deal with that. And the only way we can get rid of the h in the denominator is if we can factor out an h in the numerator. So how do I need to factor my numerator?
H2 plus H.
And that's over h, so what happens to my h's? They cancel. And as h gets smaller and smaller and smaller, then what does 2 plus h approach? As h disappears, what does this become? 2. So there's the slope of the tangent. Now, in the remaining 3 or 4 minutes we've got, we're going to be able to find the equation because we're going to do it exactly the same way that we did it in the last problem. Do we have a slope? Yes, this is M. Do we have a point? Yes, we have an XY. So y equals mx plus b tells me that f of x is the y, that's 3, is equal to the slope, which is 2, times the x value, which is 1. And all I need to do now is find b, and guess what b is going to turn out to be?
0.
Not quite, but close. Since this is 2 and we're going to subtract 2 from both sides, b is going to equal 1. So the slope of the tangent line that I'm about to draw here for you, even though mine's pretty messy because I didn't use graph paper, so mine actually looks like a secant line even though it should be a tangent line. And that's because this actually should have passed through at this point, not the one that it did. But here's my tangent, and the slope of my tangent was 2, and the y-intercept of my tangent line is 1. So there's the equation of the tangent line. Okay?
Is there a way to find that with a calculator?
Excuse me?
Is there a way to find out with a calculator?
There is, you can use the calculator to do the calculations, but unfortunately, as long as you've got that h in there, you've still got to go through this algebra. Okay? Now, before anybody gets too dismally depressed about that, because I know this is not fun. This is tedious. But it's the same process every time. What should happen every time is that when you get to this step, everything should drop out except things that have h's in them. You should wind up in the numerator with h's in every single thing that's left. If you don't, you messed up. Go back and find out where you messed up. So that in the last one, you can cancel out the h, and then when that h becomes small, then it disappears, and you'll have the answer. So we are going to continue with this. We're going to talk about this more on Thursday. But yes, you're going to have to do this. This is tedious. But the light at the end of the tunnel is when we get to chapter 12, there's an easier way. Okay? There is an easier way. Chapter 11 is about getting you to understand what it is. I will post you a practice test before Thursday.
Can you post it tonight?
I think I can post it the next hour,
Okay, that'd be awesome.
because I think I've already got the practice test from last semester.
I was on Pearson, I was able to get my accounting access temporarily now.
Okay.
But they said that for some reason, what they were trying to convince me was the content had changed. So that's why I needed a coordinator again. I was trying to explain to him, I was like, well, you know, the access coach just gave me for accounting, content's changed in that. He still just gave me an access code for that. She just kept saying, I'm sorry, you're gonna have to coordinate with your professor. I don't know if it was because of the code that was, the code that you gave me. She said it was for stats.
Yeah, I pulled it off the wrong list, and then when I went back, I didn't have any more for 1630. I've got somebody coming to see me in a few minutes, but
I'm not, you know, I'm not gonna jump on it right away. I gotta test it.
no, but I know you need to get it done. What I need to do is, I'm gonna call the bookstore and see if they can do something. Because they should be able to, I'm just gonna tell them, he was in my class last fall. I mean, he shouldn't need to buy another book, it's the same book as it was last fall. So, can you do anything just to make this good? They told us to keep a list, I kept a list, I turned her name in. I don't know why they pulled you to start with.
I always have trouble with that.
I know, we've had, and I wish, you know, when something's not broke, don't fix it.
And it's like they go out of their way to make it difficult, so you will buy another, so you will buy another.
Yeah. And that's not entirely Pearson, actually, I hate to say it, but that's mostly the bookstore.
Yeah, the bookstore.
Because Pearson's always been really good to give us, you know, extra codes for students. I mean, I've even had them, you know, where I had a student that, basically the student was homeless. He lost his house, got kicked out of his house the first week of classes, so I mean, he was a wreck. And he was broke, he had no money. And I called up Pearson, I said, look, you know, this guy's trying really hard, he's had everything in the world done to him. Can we help him out? And they sent me an access code for him and asked me if I wanted him to send a book. And I said, no, I'll give him my book, let's just get him in the game.
Yeah.
And I mean, they gave me an access code for that student.
Yeah.
So I know they'll work with us, but I just haven't heard back from the rep for Pearson yet.
I was talking to him for about an hour. I wasn't physically speaking with him, I was typing with the tech support. But,
Yeah.
Sometimes.
Sometimes.
Should I keep my eyes peeled on Provide, like the text message thing? That's what I
Yes,
saw last.
yes, because that's where I'll let you know as soon as I've got something.
Okay.
Okay?
Awesome. Thank you.
We'll get it straightened out somehow.
Okay. Thank you.